Okay, let's get back to the slide. Those of you come in late, 늦게 온 사람들, the midterm grading is open, the 한양인, do check it. I will mention briefly at the end of the class. So we were discussing on the binary trees, definition, property of the binary trees, and last class we were almost finished discussing on how to traverse a tree in different ways, right? What was 4 different ways of traversing a tree? We're gonna use the term traverse, or visit is also okay too. There were some method like a pre-order, in-order, stuff like that too, right? They just simply give you the way of what to read it first from the binary tree. 어이씨, 성적으로 좀 뭐라 그랬더니 확 쳐진 거야? 아니면 원래 아침이라 쳐진 거야? 근데 누가 잘 보고 누가 못 보고 별 문제 없죠? 전체적으로 평균이 낮으니까 다 똑같아, 점수 나가는 건. 너무 쳐지지 마요. 쳐주고 그래. 내가 잔소리하는 거 어디 한두 번도 아닌데. 그죠? Things like root, left, right, left, root, right, 그죠? Left, right, root. Different way of writing, visiting a node in the tree that is also called something called a traverse. We're gonna go back to that, and then we discussed on how to implement these trees using 2 different approaches, right? What was the first approach? What was the reason for we do a numbering on the full binary tree, numbering on the binary trees. 왜 그래? Just 3 more weeks to go. 3주만 더 버티면 돼. 그렇지 않아? 이번 주 3주, 4주밖에 안 남았을걸? 수업? 맞을걸? 이번 주까지 해서 4주니까. 그러니까 얼마 안 남았어. 힘내. What was the reason for numbering a node in a binary tree? I mean, it might be easier to store them in an array format too, right? 1, 2, top to bottom, left to right, 1, 2, 3, 4, 5, 6, that way. And then it might be easier to map those things into a array format. 그죠? But in terms of tree, we prefer a linked list way of doing it, right? I drew a bunch of figures last time having at least 2 pointers from a single node. 그죠? Usually called left, right child pointers. We follow the pointers to pointer so we can travel down on the tree and traverse everything in that path of doing it. When we discussed that binary tree, full binary tree, we kind of left this one out. What is the meaning of complete binary tree and incomplete binary tree? What was the complete binary tree? I kind of skipped through. Full binary tree, everything has 2 child in it. 그죠? That was a full binary tree. It's a full tree. If you have a height h binary tree, the number of nodes in that tree is 2 to the h minus 1, right? That was a full binary tree. What about complete and incomplete tree? Complete tree. Things on the left side is always filled up before the right side. So in terms of numbering, if you have a 1, 2, 3, 4, 5, 6, then number is right. Everything on the left side always full. Then that's a full complete tree. But if you have a tree like 1, 2, 3, 6, and 6 is not possible. 1, 2, 3, 5. Those type of trees, those called something called incomplete. So definition of complete tree, binary tree is defined by number of 1 through n node complete binary tree, 1 through n. n이 있으면 1부터 n까지 중간에 비는 숫자 없이 다 되어 있는 게 complete tree. If you do have some skip number among from 1 to n that you might call it as incomplete tree. Okay, so do not mix up with the full definition of full binary tree, complete tree, incomplete tree. If they start mixing those up, sometimes you got confused and you might follow a wrong definition of each. This is how the incomplete tree looked like. This is also on our slide as well. Something like this. I just found on the internet. This might be better. Complete binary tree. We number the nodes from top to bottom, left to right. 그죠? 1, 2, 3, 4, 5, 6. Complete binary tree. Not complete. What am I missing here? I don't have a left side of it. So 1, 2, 3, 4, 5. I don't have 6 and 7. 1 through n, but I'm missing 6. That is an incomplete tree. Also, you can take a look at it as anytime that you miss a left side of the node, then it's highly likely an incomplete tree. So that's a very simple definition of the not simple, but complete tree and incomplete tree. 저거 맨 마지막 보면 right side is 1, 2, 4. You're missing 3. From 1 to n, you're missing 3. So that is how you determine a complete and incomplete binary trees. Just in case. So we discuss array-based, and you just simply put as soon as according to the number that you give to each node, you place them into the index in the array. There were some questions, why are we skipping 0? Just to make a simpler calculation of a 0. Because we're gonna find out the number of a node by 뭐지? Left side is I, 뭐지? 2i, and right side is 2i plus 1. Those are very simple way of. Also, that's a very simple way of skipping through the elements in the array. If you want to look at it that way. So, incomplete binary tree. Also, another example from our book, figure 11.8. It's obvious the left side is always missing, and if you're dealing with this incomplete binary trees, then you might guess that there might be a lot of gaps between the elements, right? There is a lot empty gaps between the elements, so you're wasting the space in the memory array space. This just reminds me, one of the midterm questions was asking what is space complexity and time complexity. Some people wrote it like space, time. There was a definition and there was an explanation. I cannot give you the full mark. There was one small stuff that I was a bit picky about. Some 20-30% of you write it like data space. Data space. Space complexity is data space that program takes. Okay, I know what you try to say, but I didn't give you full mark on that part. I had to see that the memory space, how much memory it takes. As soon as I see the word memory, I give you the full mark. Space complexity, the time complexity, people usually get it right. Except for one special case. For the time complexity, some people start writing like a compilation. How much time it takes the program compile. I don't know where you picked that up or picked that up, but some people use the compilation time as a time complexity. Compilation time is not a time complexity. So that's just simply how much it takes for a program to run. That was a very simple definition that I was looking for. 근데 어떤 사람들 compilation time is time complexity라고 적은 사람들이 몇 명 있었어요. 그래서 조금 당황했는데 compilation은 말 그대로 프로그램 컴파일할 때 걸리는 시간이고 컴파일하고 나서 프로그램 시작을 안 하면 러닝하는 게 아니니까 혹시 헷갈리는 경우가 있었나 보다 싶어서 했는데 그거 아니에요. 그죠? 딱 틀렸다고 얘기하기도 뭐한데, 근데 그 컴필레이션만 딱 써놔서 그거는 조금 틀려요. 그렇죠? 그거는 점수를 다 드릴 수가 없다는 거 지금 말씀드리면서 이번에 점수 매기가 가장 까다로웠어. 너무 아는 것들이 많으셔서 이것저것 많이 붙여놓으셔갖고 이걸 점수를 주기도 그렇고 맞기는 맞는데 맞기는 한데 좀 어설프게 알고 있는 듯한 느낌도 좀 있어서 점수를 또 다 주면 좀 헷갈리는 부분이 조금씩 있었어. 왜 이렇게 또 힘이 없어? 정말 월요일에 시작이 꼭 이래야 되겠어? 전혀 반응이 없구나. 꿈에서 니네들이 나와. 꿈에서 니네들이. Okay, so right skewed and left skewed we mentioned. Just simply right skewed will take a lot of empty space in the array representation. So eventually they wanted to discuss the linked list way. Chain way might be better to implement this binary trees, right? And then this figure, most popular way, I drew a few examples on how to implement this. There was some suggestion, why not? Can we use a skip list to represent this trees? Okay, that's also okay too. But it's most common way, having a pointer just following each other. The total size of array, total space that it takes to implement this binary tree. Using this linked list simply means how many elements times, like n elements times how much space that single elements it takes, n times the size of each element. 그죠? Simple. And then there was some definition, class definition, and I show you some of the example to how to declare, means how to create a binary node tree. With this one has 3 different definitions, right? One, just declare nothing. Second, you declare its value, right? Elements. And the third one, you declare its value, and you also declare what's going to a left and what's going to be a right. So, element value, binary tree node left, binary tree node right. So, 3 different definitions that you can use in terms of class ways. Okay, I'm gonna skip. Visit, and then we almost finished discussing this pre-order, in-order, post-order. I think we skipped out the level order way of writing, visiting the node. So, but level order is quite obvious. What's a level from top to bottom, right? Top. I think we call it as a level 1. I think some other textbook or some stuff that you might find on the internet, they probably call it from level 0. It doesn't really matter, but for our textbook, level 1 is okay. Level 1. And then you probably top to bottom, left to right, you just follow the node. If I ask you to implement that level order, what would you use? What data structure you might use to implement that? YQ. Yeah, we will take a look at it, but it's kind of natural. As soon as I see one, put it in the queue. The property of queue is, first in, first out. So as soon as you've seen one, print out the value of the node. Maybe that's one way of doing it. That's also written our text as well. So we all know how to now implement the pre-order, in-order, post-order. Pre-order, root, left, right. So what was the common technique to implement this pre-order? What was it? Recursive, yeah? Recursive. Inside the function, something called pre-order function, you call it again as soon as you visit the root node, you call again with the left node as another starting point within the same function. Likewise, after you're visiting the left side of the node, and then you go to the right side of a node. So it's a recursive function, only require 3 lines of the code to print out the pre-order way of doing it. In order, left, root, right, post order, left, right, root. I also ask you guys to do a careful, not careful, it's a very simple stuff, but just one practice with your pen and pencil. Okay, don't just take a look at it. 눈으로만 보지 말고 just once write it down so you don't make a mistake. I think you will do it anyways for your assignment 3. I forgot to give you assignment 3 yet. I would give you sometime this week. It's not urgent. 숙제가 며칠 늦게 나오니까 편하지? 그죠? 근데 어떡하냐. 4번, 5번이 같이 나갈 가능성이 있을 것 같아. 미안해. 아니면 그런 느낌을 안 주게 해요. 4번에 5번까지 그냥 다 합쳐서 주든지 그렇게 할게요. 누가 보면 내가 나쁜 사람인 줄 알겠다. Okay, level order. The tree. I'm just gonna read this the definition of level order. The tree is processed by the level. So first, all nodes on the level I are processed from left to right before the first node of level I plus 1 is visited. So before you go down on the next level, you visit all the nodes in that level from left to right. It's the same way as putting in numbers for the binary tree. So, pre-order, visit first, pre-order, call it again, left, pre-order, right. It's a very simple way of doing it. For recursive way, I'm gonna skip. Okay, about the level order traversal, because the other 3 methods are pretty much same way using recursive, just matter of which one comes first in that inside the function. This is level order traversal for a implementation details. Before I do that, maybe I do this first. Example, for level order example, it's very simple. What sequence do I read this tree if I do this in level order way? 이건 모르면 말도 안 되고. What is it? Yeah, probably A, B, C, D, E, F, G. A, B, C, D, E, F, G, H, I, J. Yeah? Like a queue. So, let's take a look at it. I just wanted to be careful. As soon as I grading your midterms, I thought I should be careful on some of you probably not very familiar with on how to read this code from the top. So let's take a look. Void level order. Binary tree T, probably the first one I give is a root. I give a pointer where to begin with. Okay. Level order traverse of a T. Link Q. I'm gonna call my Q. Elements will be a binary tree node. That's going to be my Q. So I just create a Q. Oh, nothing in it yet. Q가 이렇게 그리면 안 되는구나. Q. That's a stack. Q. I have a Q. Empty Q. While T is a null T, let's say this is my tree. Probably I'm pointing T right here. While T is not null, but from the beginning I already tell T is here. But I see that T is here, so it's not null. I can continue on that loop. While T is not null, empty, visit T. A, B, C, D, E, F, G. Visit T. Okay, what was the meaning of visit T? They probably in this code they usually put it as a print A. And then start checking if T's left child, if T's left child, it's also a way of checking if T's left child is null or not. 비어 있는지 안 비어 있는지. Do I have a left child or not? Okay. T's left. What am I looking at? T's left. But this is not null. It's something there, some node are there. And then it says Q push T's left child. I'm pushing it. I'm sorry. Push pop is more of the term in stack, but same way. Push, add left child B into Q. Right? That's what I just did. Okay, done here. Next line. If T's right child is not null, T's right child, I see that as C, so it's not null. So I can do this. If it's not null, then Q add right child. See? 그죠? Am I in the right track? Okay. And then next step is something doing something. But what should be the next step just without looking at that? I just check whether I have a left and right child. I put them in my queue, and then in the level order, I should print them out first before I go on to the next level, right? So probably the things that I should do at this step, at this moment, I probably check my queue if I have anything to print out. That's what it does. That says try T's Q front, Q front. What's a Q front? What was this function is returning? 뭐였지? 이거 뭐였지? 뭐 있는지 없는지 Q 값 제일 앞쪽에 있는 값 보는 거였죠? 그치? If you remember the definition, some of the operations in the queue, I think Q front, this function just check whether you have elements in the front. I mean the contents of the elements in this location. This location. Try Q 뭐야 어디 갔어? Q front. Get the value and the position at the front of the queue, which is B, and checking if Q is empty, error. Otherwise, Q pop. Simply Q remove. But when you remove the elements from the queue, you always remove the first elements, 그죠? As soon as you pop, B. Try this until you pop it out. C. 오케이. 근데 여기서 좀 미싱하는 게 있는 게 이 다음에 어디로 갈지 알려줘야 되는 거. 그것도 T를 매번 이걸로 가르쳐 주니까. T 이렇게 가고 이렇게 또 가고 same way. Okay. So if I do this, I probably don't that try and catch. Might be confusing for some of you. I will just do the looping again. Okay. So that's the basic idea of using Q in order to print out this elements in the level order. So it makes sense, 그죠? 말이 돼 안 돼? 말 되죠? 아니면 어떻게 해야 되지? 모르겠다. I don't know how to do it without the queue. Maybe there's better way. But if you find out, then let me know. So space and time complexity. The space complexity of each of the 4 traverse algorithm is order n. The time complexity of each 4 traverse algorithm is theta n, that's order n. Why? Because you are eventually visiting every single node in the tree. So it's still a big O of n, big O of n. 어차피 n 개 다 갔다 가야 되잖아요. 그죠? 그러니까 worst time case is still big O of n. You're dealing with the n element in the tree. 스페이스 컴플렉시티 링크 리스트 하니까 n개 노드를 메모리에 가지고 있어야 되니까 어차피 이것도 n. 트래버스 하는 거 걔네 하나하나 다 프린트 해야 되지. 어떤 순서로 가든지. 그죠? 그럴 바에 어차피 n개를 다 한 번씩 가야 되니까 still n. So it's still big O of n for both space and time complexity. Okay? But we care mostly for time complexity. Space complexity here can be varied. I mean, we're just simply using a linked list. Linked list! Why are we using linked list for binary tree implementations? What happened if we use array? 아, 힘들어. 가만 있어봐. 머리를. 아까 전에 봤을 때 트리를 array로 저장을 했을 때 array의 문제점이라고 나온 게 하나 뭐였어요? 중간에 너무 빈 공간이 많을 수도 있다는 거였죠. 그래서 제일 좋은 거는 링크리스트로 트리를 구현하면 내가 만약에 트리에 n개 노드만 있으면 n개 노드만 만들면 되잖아. 그죠? 그 얘기야, 그 얘기. n개만 만들면 되는 거. 그 얘기예요. 그리고 트래버스 하는 게 내가 왔다 갔다 하면서 하나씩 찍어야 되지. 어떤 순서로 가든지. 그럴 바에 어차피 찍는다는 게 한 번씩은 다 가야 되잖아. n개. 그러니까 big O of n. worst case는 어차피 다 한 번씩 안 가면 어떻게 찍을 거야? 다 찍어야 되는 거야. 그 얘기예요. 그 얘기. So I think that might be the end of the binary tree ADTs. We did take a look at some of the abstract classes of the binary tree node. Of course, this is not the only way. I mean, you can certainly define your own node trees, own node. According to your own definition, you can build your own trees. I mean, even for my own node definition, I add one extra pointer. Always my extra pointer in the node definition of mine. Ancestor, yeah, I think I add just ancestor, one more pointer that's going back up. Just in case, if I need to go back up. I don't want to go from top to bottom again. I mean, it might be easier in some cases. So you can define your own node trees. The one on your textbook and our slide is not the only way. According to that tree node abstract classes, you can certainly define your own operations. That's what ADT is about, set up the data structure and the set of operation that you can perform on that data structure, right? So, and different type of implementations. I think you should know how to implement the pre-order, in-order, post-order with the level order. So simple type of pseudocode that you need to know how to write it, how to use it, how to read it. Time complexity here is quite obvious, as we discussed. So read section 11.1 to 11.8. But I do take a look at it again yesterday. We pretty much cover everything. So in terms of reading, there will be very less things to read. 그렇게 읽을 게 많이 없을 거예요. 수업 시간에 많이 얘기한 게 있어서. Any other questions? I don't want to go back to this binary tree again. Simple trees. Yeah. What was the difference between tree definition and binary tree definition? Yeah. One can be not empty or not empty. It's okay. Those type of stuff that you should remind yourself. We'll get back to you right away in the next chapter. What chapter is this? What's the chapter number for this one? Priority queue and heap. I forgot. 몇 번이야 chapter? Data structures. Priority queue and heap. Priority queue and heap. So And sometimes you might want to remember your high school days and maybe an hour before your final exam, study like your high school kids. It might be get you a much better mark than your midterms. 그죠? 고등학교 때처럼 공부했으면 기말고사 다 맞을 거야 아마. So do your stuff. So without knowing with the binary tree, full binary tree, it may not be possible to understand the stuff that we will discuss in this chapter, especially for those hips stuff. Hip is basically also another tree-like implementation. So you need to understand the basic properties of a binary trees and how to add a node, remove a node. Those are the very basic operation using this hips. Priority queues first. We know what priority queue is, right? Queue is first in, first out, but I try to give a priority of each element in that queue. And sometimes I break the rules. Sometimes, instead of taking out the elements from the queue, the longest waiting one in the queue, no. I would probably take out one maybe at here first, based on priority, 중요도. So it's another way of taking out the elements from the queue. That's what's called that's a very basic idea for priority queues. A priority queue is collection of zeros or more elements. Each element has a priority or value. Very simple example for priority queue. The next slide probably asking you what might be the real world example for priority queue. We give you one example in real world for priority queue and another example in computer ways. Okay. Unlike the FIFO, first in, first out queues, yeah, the order of deletion from the queue, order of taking out elements from the queue is decided by a element's priority. So in this way, I may give another value. This is my queue again. C, F, G, H, Z, I. This is front, end. Normal ways, I would just take out the C first, and then F, Q, B, Z, Z, I. But this time, I give a special value. C is 10, F is 100, Q is 1000. 2, 3, I don't know, 50. I give a special value this time. So if I want, I'm going to tell this queue, take out the highest value in the queue. So I do the sorting. I see that Q has a 1000. Take this one first instead of C. That's my priority queue. And I can give a separate values to determine which one go out first. So it's a deviation of the queue, right? Deviation of the queue. Elements are deleted by increasing or decreasing order of a priority rather than by order of in which they arrive in the queue. So if I want, I can sort these values, maybe the biggest one first or smallest one first. That's up to me. That's up to situations, up to your implementations. So that's something like this is possible. That's what priority queue is about. 쉽죠? Operation performed on the priority queues. Find an element, insert a new element, delete an element. Well, it's not so much different from a normal queue, right? Just one more thing to consider this time, the priority value, special value this time. So two kinds of priority queue exist. One, mean and max. If you take out the elements, what the minimum value, minimum priority value, probably minimum priority queue. If you take out the largest one first, probably a maximum, max priority queue. Mean and max priority queue. Of course, there are other smaller different queues out there. but this is the things that we will cover here in this chapter. In a mean priority queue, find and delete operation finds and deletes the elements with the minimum priority. Minimum priority. Whatever reasons are. 뭐 때문에 그럴 수도 있고 아닐 수도 있고. In max, opposite. You take out the elements with the maximum priority. 2 or more elements can have a same priority. So priority can be duplicated. I mean, C and F can have same priority value. Which one take out the first? Maybe just pick one. If they have a same priority, it doesn't really matter. If you look at this approach carefully, what can you do using this priority queues? What might be the possible application of using this priority queues? Just wild guess. You can take out the elements based on some value, ascending or descending order. Maybe if you can adjust these values nicely, yeah, we can do some type of sorting. 숫자 정렬하는 데 쓸 수도 있겠죠, 그죠? If you take out the minimums first, then minimum, take out the one is the minimum. Among the leftovers, you take out another minimum. Among the leftovers, another minimum. Then it goes like a 1, 2, 3, 4, 5, 6. Another sorting example is possible. Sorting is possible with this priority queues. Maybe. Likewise for the max. You can also start take a look at the ADTs and programs in 12.1 for max queue priority queue specifications. If you start looking at those stuff, what might be the difference between max and mean? If you wanted to find out the mean priority queue specifications implementation, 뭐만 바뀌면 될까? What would you change? Yeah, I'd probably just change this direction of the inequality signs. 뭐 이거면 반대로 바꿔주고. Or if they use a mean function, you can just change to a max function. 그죠? 그만 바꾸면 뭐 땡이겠지. 그죠? So it's pretty much same. Please start reading 12.1 and 12.2 examples, but these examples not so much different from this number ones. They try to give you the idea for having a priority values on each element. What are the examples in our daily lives that utilize priority queue concept? I give you already one, maybe sorting. Priority queue. What if, when we're discussing a queue, I give you one small example, one small simulation example on supermarket. 그지? You remember? No? Yes? No? Supermarket. I draw a cashier example. 이렇게 해갖고. People waiting in the line, go. How much time each cashier it takes, you can simulate how many queues that you might need. 그죠? there might be 100 customer waiting. Then if you use a 3 cashier 이렇게 하자. 하나만 하자. Q로 하니까 좋을 것 같아. Cashier. Each is a queue. Then maybe with the 100 customer waiting, this would give me about 20 minutes to serve all the customers. If you add one more cashier, 이거 찍어주는 아주머니 한 분 더 계시면 maybe the time reduced maybe 10 minutes or sometimes even worse. I don't care. Okay. That's the example we discussed in the queue examples, right? What if you adopt this approach in the priority queue? 이거 뭐 다 때려치고라도 maybe among 100 customers, I select out the customers that has the largest amount of a element shopping list. 많이 산 사람. I take out those customers out of this line and put them in the special queue. right? It will reduce some waiting time. 오늘 너무 일찍 들어오시네. 어? 짱 일찍 오는데. 수능 봤어? 아니야? 뭐야 어디까지 얘기했지? The customer with many things they buy, then put maybe one goods, 1 point. If they have 100 goods to buy, they have 100 points. I take out those customers to a special lane or something. That might reduce a entire waiting time for average waiting time for the customers. Maybe different ways of doing it. Or priority is often used in 어디서 많이 쓰지? If you try to take a plane. 어디 비행기 타러 가면 막 사람도 서 있고 하는데 가끔씩 장애인이나 나이 드신 분 앞으로 빨리 나오세요 그래갖고 앞에 싹 껴주잖아. 비행기 안 타봤어? 미안해. 비행기 말고 난 비행기밖에 생각이 안 나서. 비행기 말고 또 뭐가 있지? 모르겠다. 그래 비행기 그런 게 있대. 보면은 애들이랑 임산부 먼저 태워주는 거 그런 거 보면 돼요. 뭐 지하철도 마찬가지일 수 있어요. 지하철 안에 임산부석, 노약자석 따로 있는 것도 뭐 그것도 자리가 3개 이렇게 있잖아. 그것도 프라이어티지. 앉아있다가 하나 툭 일어나고 새로 껴주고 하는 거랑 똑같은 거예요. The kids and seniors have a higher priority because they are vulnerable or something. Whatever reasons they have. Okay, those are the simple examples. Or in your computer systems. Some programs running, probably multiple programs running in your operating systems. 그죠? Sometimes you turn on Explorer, same time you turn on Microsoft Word, sometimes you turn on your games at the same time. Each one has a different response time. Sometimes they need immediate responses from you. I need to click on something right away. So they pop it up. That's a priority. That's a priority that is given by the operating system. So I have to respond. They break out the rules. 그냥 OS 자기네들 윈도우 쓰고 이렇게 하잖아. 그러면 윈도우도 띄워놓고 워드도 띄워놓고 뭐 게임도 띄워놓고 이러잖아. 동시에 막 하고 있는데 중간에 어떠한 프로그램이 갑자기 팝업을 툭 튀어가지고 이거 빨리 체크해 주세요. 뭐 할 건지 말 건지. 뛰는 순간 그것도 어떤 개념적으로 보면 프라이어티예요. 자기네 윈도우에서 얘 먼저 해야 돼 하고 큐에서 먼저 끄집어낸 거예요. 얘 먼저 대답을 줘. Same way. Similar concept is being used when they scheduling the programs in your operating systems and stuff. So things are priority based ones. Okay. So how do we implement this? Implementation of a priority queues. Implementation of a priority queues. Implemented using hips and leftist tree. 2 ways. If I wanted to implement this priority queue, 2 ways. Hip, something called hip, and leftist tree. Definition of a hip is a complete binary tree that is efficiently stored using the array-based representation. So it's not a linked list, array-based representation for complete binary tree. What was complete and incomplete again? We discussed, right? It's different from full binary tree, or it's not that. You have to have a certain orders, 1 through n. If you're missing an element among that, then it's an incomplete tree. But hip is a complete binary tree. Leftist is a linked list data structure suitable for implementation of a priority queues. Priority queues. Okay, so maybe also 2 ways. One using array, the other one using linked list. When you try to implement this priority queues. 슬슬 집중력을 잃어가십니다. 원래 없던 집중력이 이때쯤 되면 더 없어지는 것 같은. 정확하네. 강아지들을 트레이닝 시켜도 정확하네. 똑같네. 원래 수업 시간에 한 50분 정도가 더 맞지 않을까 싶기도 해요, 사실. 그쵸? 고등학교가 50분, 10분이라며. 평생을 그렇게 사셨으니 50분이 맞겠지. Mean and max and mean tree. Max tree, mean tree, or mean tree is a tree which the value in each node, we are taking a look at a heap now. So, which value in each node is greater than or equal to those in its children, if any. Mean tree, exact opposite. Let me see. The value in each node is less than or equal to those of its children. So I have some value, my value is 10. My children will have a less value than 10 or larger value than 10. That's a definition of mean and max tree. Mean or max or mean tree. Okay. When you see these figures, it's much more clear. Just that's it. I mean, only one property they have to follow. If it's max, then it should be greater. If it's less mean, it should be less than what I have. Node of the max or mean tree may have a 2 or more children. May not be a binary tree. So it's a slightly off a definition of a binary tree. So mean max tree itself doesn't have to be a binary tree. So later they call it as max binary tree, mean binary tree. Then it's a binary tree. mean max tree만 놓고 보면 binary tree는 아니에요. 뭐 세 개도 낼 수 있고. 근데 나중에 mean binary tree, max binary tree라고 따로 얘기를 할 거예요. So simple as this. Root has the maximum element. This is max tree. One of the top elements on the bottom, the value of the under the root cannot be greater than value of a root. Likewise, 4, same rule applies. The children of this node cannot be greater than the value of a root. I mean the parents. They can be same though. I mean it can be duplicate. 8, 7, 3, 1. 그죠? Always less than its parent. That's a definition of max tree. Mean tree, probably exact opposite. 그죠? Root has a minimum element. The next slide. So if I start taking elements out, I know that the one on the top has a maximum value. What happens if I take this one out? Maybe I need to figure some ways out to get the maximum value among the leftovers and then put them as a root again. So, okay. If I are allowed to take out the root values. 내가 만약에, so I like to get the maximum value of this entire tree. I know that root has the maximum one, let's take it out. So I take a look around the tree again. Because I'm missing a root, I need to put something on the top again. Take a look around. 9 seems to be on that next biggest one because it was equal as the biggest one. Maybe I'll put it up here. But how? How we can implement that? In this max tree with there's no node, tree node control, then it might be a bit difficult. But hopefully it might be a bit more simpler when you're using a max binary tree or mean binary tree. If I start doing it like that, so it's another way of doing a sorting, right? I mean, that's what we are going for in priority queues. 이것도 mean tree. So there will be a very simple questions like you're given a tree, find out whether the tree that you have is a min tree or a max tree. Then you might need to go through the list intervals around the tree and find out whether they satisfy the condition Depends on whether they're max or mean. Well, that might be a reasonable algorithms out there to test whether your tree is mean or max. 사실 나중에 나오는 게 그게 다야. 여기서 하나 툭 떨궈냈을 때 계속 예를 들어 계속 여기서 미니멈만 하나씩. 2, I know it's minimum. Take out 2. Among the leftovers, 1 might be the minimum. I just look at it through. 3 seems to be minimum. Put 3 up here. 그렇죠? 그런 식으로 하다 보면 틀이 계속 없어지면서 제일 작은 값이 툭툭툭 바깥으로 나가면 소팅이 자동으로 되겠죠? 그렇죠? 하나의 예제로 나중에 쓸 수 있을 거예요. Hips definitions. Max hip. So it's a definition of a hip. A max hip is a max tree that is also a complete binary tree. Okay, that's a definition of a hip. Now, max hip is a max tree that is also complete binary tree. So it's a complete max binary tree is a hip. Okay, complete max binary tree is a hip. Another name for that is a hip. Okay, take a look at the figures in 12.1, 12.2, A and C for max and min hip. Definition of complete binary tree I also explained in the beginning of the class today. So you can certainly take a look at page 427 for complete and incomplete binary trees, especially those of you who come in late today. Do take a look. Some of the examples out there. Okay, I think I'm gonna stop. 아니야, 이것만 보고. Okay, 14, 12. Yeah, I think I'm gonna stop here as well. This is the figures that is also in your textbook as well. Before I stop, those of you who came in late, I put up the assignment mark. Not assignment. The midterms. 이거 I put it up in the 한양인. Average was 54. The highest grade was 88. So do take a look at it. I explained a little bit as well at the beginning of the course, beginning of the class. 나 오늘 왜 이러니? 헷갈리니? Okay, do check it. If you have questions, talk to me. Forgot. If you want to check out your paper, 이번 주 다음 주 월요일 괜찮아? 다음 주 월요일? Next Monday afternoon, is that okay with you guys? Next Monday afternoon. If you want to check your papers, then come to my office next Monday afternoon between 5 and 6. Between 5 and 6. 5시부터 6시 사이에. 5 and 6. Okay? Okay. I'm going to call out the attendance now.